Hello everyone. In this video, we're going to learn how to fine-tune a large language model for your own task with any custom training dataset. In particular, we're going to fine-tune the Llama 3.2 1 billion model, which is one of the most lighter weight language models around, and we will be using Huggingface and Pytorch to fine-tune this model on a very interesting classification task. Along the way, I will show you how each step of this fine-tuning process works, what pitfalls to avoid, and go from concepts like prompting and loss calculation to low rank adaptation and everything in between, and how you can basically write any custom training loop for fine-tuning large language models on your own locally. Because it's a machine learning channel, I wanted the training task to also be kind of relevant to machine learning. The task goes like this. We input an archive ID of a paper, and from this ID we want to extract the title and the summary and then pass it into an LLM to output the category of the paper. And obviously for fine-tuning you first need training data. So I use the archive API to collect 2000 of the most recent papers in the computer science category and then create a dataset that contains the title, the summary, and the string representation of what this category is all about. Our goal is to pass in the title and the summary and output this category field from the LLM. Now, technically you don't need to fine-tune a language model to do this task, but for the sake of this video, I'm going to pretend that we are not allowed to use few-shot prompting and we are not allowed to train our custom neural network from scratch. We're just going to be limited to fine-tune a language model, and hopefully by doing this, we learn how to fine-tune language models. And trust me, if you learn everything in the video, you can pretty much apply the same concepts on any training task, not just this one in particular. Huggingface provides some open source tools that allow you to train neural networks and also use open source neural networks very easily. In particular, Huggingface has a library called Transformers, which I'm sure you've heard of if you're in the NLP space. Transformers are a library that provides APIs and tools to easily download and train state-of-the-art pre-trained models. So you basically specify the model ID, which is the Meta Llama 3.2 1 billion instruct. And here we load in a tokenizer and a model. I'm going to explain what these things are in a minute. And so what happens internally is that Huggingface downloads this model from the Huggingface model repositories and loads it into our system. Now, because I've already run all of this before, it's not downloading the model, it's just loading it from disk. But when you run this for the first time, it will be downloading a model from the internet. So as you can see, the model is an auto model for causal LM. It's kind of interesting to understand what this causal LM thing stands for. LM basically stands for a language model. What's a language model? A language model is a neural network that is able to form a probabilistic model of text or language. Basically, given some sentence, it can predict what the probability of that sentence is. Now, there are different types of language models like masked language models and causal language models. What causal language models basically do is, given a prefix sentence, it tries to predict the next word in that sequence. Being a causal LM basically means when the new tokens are getting generated, it only depends on the tokens that has come before it. If you want to learn more about these concepts of transformers and language models and all of that and attention, you can check out these videos where I cover them in much more technical depth. And next we have this thing called the pipeline. The pipeline is, again, it's an abstraction of how an LLM works. I'm going to explain how exactly that works, but for now, just kind of think of it as a black box where you pass in a string and out comes a generation. Now, if I do this and run this, it's going to be generating a text. And as you can see, the prefix of this text is the input that we had sent in, and then the LLM has, generated more stuff. I'm a friend of friend. I heard that you're a bit of a troublemaker. What? Anyway, hope that makes some sense. Now, another thing to understand is that you can pass in a list of strings as well. Like here, we just passed in a single string, but in general, you can pass in batches of strings, and that will output a batch of responses. So with that high level understanding out of the way, let's dive in a little bit deeper and look at what exactly is happening when this pipeline thing is running. What's happening under the hood? Well, the first thing that happens is the pipeline tokenizes the input strings. Basically, given this string, it's going to break it up into tokens or words or subwords, and then given those subwords, is going to convert them into integer token indices. Let's see how that's done. So we have the input prompt. In this case, we just have 2 strings. So if you just pass tokenizer input prompt and play this, you basically get a new input of shape 2,6. Let's have a look at what this thing actually is. So it's a bunch of integers. Basically, the thing we had passed in has been converted to this thing. So this hello has been converted to 9906, how to 1268, r to 527, and so on, and similarly capital to 791, and so on. Now we sort of lucked out because these tokens are the same length, but something bad will happen if we change this a little bit. Well, now you're saying that we are unable to create tensor, you should probably activate truncation. So what's happening under the hood is, because we added a new token, this first entry, this first list of tokens has now expanded. It was 6 before, it's 7 now. Now, because of that, it's not able to form a tensor because the tensor needs to be rectangular. So for that, what we're going to do is we're going to pad this thing. One way to do this is just say padding underscore side equals left. And here we're going to say pad equals true. Is it pad or padding? I think it's padding. Well, now it's saying for something else. The tokenizer does not have a padding token. Well, this is also pretty simple to fix. We are just going to say tokenizer.pad token equals tokenizer dot the end of string token. A lot of these language models don't come with a pad token off the shelf. So to do padding, you basically have to say that the end of string token is the pad token. And now if we run this, indeed it's 2,7. And if we print this out, we see something interesting happening. The first one is fine, but in the second one, we have a new token, 128009. Now, what this is basically that padding token that we had inserted. So if we add more stuff here, this thing is going to still run and it's going to pad more and more. Now, you might also wonder what this 12800 is. Well, let's try to convert these integers back into the string formulation to see what they are. To do this, you can do tokenizer.batch decode and then pass in this tokenizer input IDs into this. And here you see what it is. Now 12800 is basically this special tag called beginning of text, which basically means that everything will start with this beginning of text special token. Now another interesting thing is if you look at the tokenized object in general, there's actually 2 things that are there. The first is the input IDs, which we had been seeing, but there's also this thing called the attention mask. Well, let's have a look what this attention mask is. The attention mask is basically a binary mask where you have 1 everywhere where you had an actual token and 0 where you had a padding. To explain it in very simple terms, by setting an attention mask, you tell this mask attention block to not give any attention to this padding tokens. Just only give attention to beginning of text, the capital of and India. No need to provide any attention to these because they are just padding and it's there so that Pytorch does not fail when we try to make a non-rectangular matrix. So the next thing I'm going to talk about this thing called chat templates. So language models do this thing called instruction tuning, where basically after the language model is pre-trained using next word prediction, people fine-tune these models on instruction prompting. Basically what happens is that these developers, they create large data sets of instruction and what the model should respond for that instruction. So suppose we have a prompt that looks like this. You have a system prompt that asks the AI assistant to speak like a pirate, and then the user just asks, where does the sun rise? To convert this into this kind of a string representation, we have this thing called apply chat template. And I'm going to explain what these things do in a second. But let's sort of see what happens. So if we run that function that I just showed, it basically converts this whole list of dictionaries into something like this, a string representation where you have a beginning of text and then you have a start header ID for system, and then you have some information that the meta people just force inside the prompt, and then we have the prompt that I had written here. And after that, you have the start header ID user, end header ID, and the question, where does the sun rise? And finally, you have this additional thing that I did not mention. It says assistant. So basically what it says that given all of the things, now you are going to insert this entire thing into the LLM, and then the LLM should predict word by word what happens next in the sequence. Now obviously this entire thing is a string, but to pass it into the model we need it as integers, right? So for that we actually just needed to turn this tokenize equals true. And if we did that, now we have integer tokens that we can easily insert into our model, and in the next column that's what we'll do. And then let's just convert it into a string. Well, yeah, it did convert into a string, and you can see that after this start header ID, assistant, end header ID, the model started, generating new things as a pirate. Another interesting thing is this flag called the continue final message. Now, sometimes you want the assistant to begin the sentence in a specific way. For example, we want it to start as II. So what we're going to do is we're going to say II here. Let's see what happens if you run this. Well, interestingly, you'll see that it says start header ID assistant II end of the text, and then again a different message starts, but we don't want that. So let's see if we say add a generation prompt to false, because the add generation prompt, what it basically does is it adds this entire thing to the tokenized prompt itself. So if we turn that to false and run this, well, now you have II, but again you have the end of text ID. We don't want the end of text ID at all. We want it to generate new stuff after II. So for that, what we could do is say continue final message equals true. What that means is that you want the LLM to generate from here. So there's no end of text ID at all, as it was in that previous example. You want the LLM to start generating from right here. Now let's see what happens if we turn this to true and then run that entire thing that we wrote out earlier. And while that's running, let's copy this as well. Yeah, and you can see that it says, "Hi matey, you're asking about the sun rising place, eh? Well, it's gonna say more things if I increase the max new tokens to say 56 for whatever reason. Let's run it for a bit. It's gonna take some time. And if you run, yeah, it says a lot of stuff. Okay, that's right, the east. Okay, so hopefully that sort of unpacks what this pipeline thing is actually doing inside the hood. There's still a lot to unpack about Huggingface and Transformers and all of this, but let's sort of parallelly work towards our archive goal. So what I've done is I've created this dataset right here that contains the title, the category from archive, as well as a string representation of this category. And it also has some other things like when it was published. I made sure that all of this was published after the cutoff training date of the LLMs. And you also have the summary, which is basically the abstract of the paper itself. And again, the goal is to write a prompt that inputs this title and the summary and outputs the category description. Let's see how far we can get without fine-tuning with just simple prompt engineering. So here I have written a system prompt. The system prompt basically looks like that. You can feel free to pause and read. And then you have these user messages, which basically tells the LLM what the title and the abstract is. And if you print the entire prompt dictionary, it looks kind of like this, where you have the system prompt, which is going to contain that system level instruction. Then you have the user prompt, which is going to have the title and the abstract. And you have the assistant, which is going to start its sentence by saying labeled category, and then it's going to generate the rest of the outputs. And here I have tokenized it using the chat template thing. I've crucially said continue final message equals to true, and let's see what that looks like. And here you have a bunch of things. Obviously it also contains everything of the prompt as well, so let's just extract the actual labels instead of printing everything out. And yeah, and here you see artificial intelligence, computer vision and pattern recognition, computer science, machine learning. You can see that for some the prompt also outputs some garbage. And actually if we looked at the original categories, the category description, it was computer vision and pattern recognition. Well, it says artificial intelligence, which is not correct. The next one is natural language processing. It again says computer vision and pattern recognition. And so it's not actually doing a good enough job. But let's run it on a larger data set and see what these outputs are going to look like. So like any good machine learning engineer, I created a train and a test set from the input CSV and then ran the test set through this LLM to generate the outputs. From the look of it, you get around 40% accuracy when you run this 1 billion parameter model untrained on this dataset. In the next section, we are slowly going to explore how to improve this using fine tuning. Also, if you're enjoying this video, please do make sure to subscribe to the channel and hit the like button because it helps out a lot. Do check out our Patreon because I'm going to be sharing all of the code, all of the slides, everything that goes into this video and all of my other videos on that Patreon channel. And finally, a huge thanks to all of our Patreon members and the YouTube supporters. You guys make this channel tick and I'm very thankful for your support. We are closing in on 10,000, so I'm very excited about how the channel is going to grow in the future. So thank you, and let's get back to the video. When we are using a language model during inferencing, we just have the prompt or the prefix sentence, right? And we generate the next token and we pass that back into the LLM to generate the token after that, then pass that back in again to generate the token after that, and so on and so forth. Autoregressively we generate the entire sentence, right? The problem with this approach is that you can't parallelize it because every token depends on the generated token before it. You have to generate the token before it to generate the next token, right? Well, during training, attention-based models employ a different technique where they can parallelize the learning of the causal relationships between the tokens. So the way transformers inputs and output works is that you input a sequence and you output a sequence, and the output sequence is sort of shifted 1 unit in the future. So if you input to the LLM hello, how are, the expected prediction will be how are you. If that did not make any sense, I promise you I'm going to show exactly how that works. Right here we have the text as hello, how are. Now hopefully if we pass this sequence into the model, it should predict hello, how are you, because I guess you is the most probable word after hello, how are. So again, we have the text, we tokenized it and we passed it into the model. Now notice that we did not call model.generate. We passed it in directly. So if we printed out.logits, you basically see a lot of numbers. What are these numbers? Let's see if you did a shape. Well, it has 1412826. Well, the 4 is the sequence length. So if you look at your input IDs that you sent it into the model, it had 4 tokens. The beginning of sentence, hello, how, and are. What's 128256? Well, that's the vocabulary size of the model. Basically, so if we are looking at the last index and if a value is high, the chances of that being the next word is also high. So if you look at the tokenizer and you did convert IDs to tokens and we'll say 100, this basically means the 100 token looks like that. The 25th token looks like a colon. The 450th colon is IZ. And if we took this and printed 450, basically says that actually before that, let's convert it into a probability distribution. So probability is equal to nm.softmax out.logits 0 minus 1. Okay. So it says that the probability of IZ being the next word after hello, how are is that low. It's 10 to the power minus 9. Now let's see what is the probability of a common word like, you. Well, to do that, we first need to find the ID of you. So it's 9514. So apparently this is also low, 10 to the minus 6. That's weird. What if I added this G thing here? Now it says 499. Let's see of that. This is very high. It's 0.98. It's almost 100%, almost 98% chance that this is the next word. So what did I do here? Well, this G is a special thing that we have in llama models. These two things are different. How are they different? Well, this GU basically means that there is a space before U, and this means there is no space. Say we have a string called text equals to U. There's no space here, you have a colon and U. Let's see what that returns. Well, this returns 9514, which is this guy. But let's see if we had a space here. Now it returns 499 because you have a space. It is now different. So what we should do is find the maximum, the argmax, actually the index with the maximum value of that output logits, and we want to say the axis is -1, and that returns is this new sequence. And obviously we just care about the last value because we just want to find the next word, what comes after hello, how are. And the last one is obviously, as you can see, is 499, and if we just get the last value of that sequence, that's 499, and if we just converted that, tokenizer dot decode, and you have U. So the next word should be a space U. And obviously if you run this thing again, you now get a new sentence today. And I hope you understand what's going on here. You're basically running this in a loop, and that's how the strings are getting generated. If you want to fine-tune large language models, the goal is to give it input sentences and then make it learn the sequence. For example, suppose we want the LLM to learn the sequence subscribe to neural breakdown with AVB. Basically meaning if we input subscribe to neural, then it should output breakdown with AVB. Let's see step by step how that looks like. So first it's going to be tokenized, and here are the tokenization integers and how they look like after decoding. The interesting thing is that given this sequence and their tokenizations, we can extract the input sequence and the target sequence from this tokenized sequence. If we take the sequence from the beginning to the last but one element, that will be our input, which looks like this. And if we took from the second index to the end, that will be our target sequence. Basically, this means that we're going to input this sequence into the transformer. The transformer is going to apply its causal mask detention, and the corresponding outputs for each of this token is going to be its next token. So for 128000, which is the beginning of text, we want the neural network to predict subscribe. 29673, we want to predict 311, which I think is 2, and so on and so forth. So that's the goal. And obviously we can apply the same to the chat template idea. So suppose we have a prompt that looks like this, and we have the answer to this capital of India question. If we do the chat template on the prompt, we have the string representation of the prompt, and then if we just add the answer to the prompt, then we have the entire sequence that we want the model to learn. We basically want to pass the model this entire sequence and let it learn on its own. So again, if we tokenized this entire string, this entire prompt and answer pair, we get this sequence. And if we extract the start to end -1 and start +1 to end, we get the input IDs and the target IDs. The input IDs obviously is everything up till here, and the target is shifted by 1 to the right. So it's that. Basically, we're going to input this sequence, and whatever the LLM outputs from here, we are going to calculate the loss between the network's output and this target that we want the network to predict. And depending on the loss, we are going to backpropagate through the weights of the network to update it so that it generates the correct sequence. Now, in reality, we are going to use a LORA adapter, which I'm going to come in some time. But at the end of this notebook, we are going to still train a network to output a specific phrase. So I promise this notebook is going to end with something nice. So if you look at the target IDs, another interesting thing about this is that it also contains the prompt itself. So if you remember the original prompt, it was actually up till here. So this last 3 or 4 tokens is what we want the model to predict. So ideally we would want the backpropagation loss to be calculated just on these 3 tokens, not the entire sequence. So for that, we need to identify which of the tokens are from the answers and which of the tokens are from the input prompt. So let's see how we can do that. First of all, let's just tokenize the answer. So if we tokenize it, this comes 15612267, which is the last tokens of our input IDs. We also want the end token to be captured because we want the answer to finish. We want the model to stop generating after it outputs the answer. So for that reason, we are also going to add the tokenizer dot end of string token. We are also padding the token to the max length, and the max length we are choosing is the length of the input sequence. So here the length, so if we calculate the shape of this input token, it's of 43 tokens. We also want this label tokenized to have 48 tokens, except everything is prepended with the padding token. So if you remember, 128009 is the end of string, or in our case the padding token. And finally here what we are doing is that we are turning all of those tokens into -100. Now this -100 thing is a special thing that the llama documentation suggests you to use when you want to mask it when calculating the loss. I'm going to talk about what exactly the loss calculation is here in a minute, but if you just kind of look closely, everything that was padded is now -100. We don't want the last token to become a padding token. We want it to remain the end of string token. That's why we're going to manually set that the end of string token. So now we have this sequence. So this is going to be our target sequence. Anyway, so if we wrap all of that into this function where we can input a list of prompts and target responses, and then we calculate the chat templates, and we would basically have a function where we can pass in a prompt and a target response, and it will output us the input IDs and the input labels. Next, let's think about the loss function. Well, the loss function is pretty simple. We already have the labels here. Now we just want to pass the inputs through our neural network. The predictions that it generates, we want to see if the corresponding indices were picked or not. So first off, we do the output calculation where we have the logits of shape 1, which is the batch size, 43 is the sequence size, and 128256, which is the number of words or tokens in our vocabulary. And we have the data labels that we had already shown before. And then to calculate the loss, I'm just using a good old cross entropy loss. The cross entropy loss, basically it takes a probability distribution, which in our case is this out.logits thing, and it also takes the target labels as these indices that should be the target or desired labels for those. Like for example, if we did shape here, it is 1,43, which is the indices of the 43 tokens in the sequence that should have the highest value, and then it applies the cross entropy loss to calculate how close it is. So if we did that, then we're gonna see the loss. So let's see, we pass calculate loss, and for the logits we will pass in out.logits. So for that you can see that the loss has only been computed for the indices which are not -100, and you can see that the loss is pretty low because the model already knows that the answer is New Delhi. But let's see what would happen if we wanted the target to be some other city, not New Delhi. For example, suppose we want to force the model to output Mumbai when we ask the capital of India, which is obviously an incorrect answer. So because these models are already pre-trained, you will hope that the value of Mumbai is going to be higher. So if you did the calculate loss, you can indeed see that now the loss is higher. It's 6.2297, and here it was in 0.0s. So that kind of suggests to us that depending on how different your fine-tuning data is to the original model's outputs, it's going to change the network weights more drastically depending on how far it has to move its weight to accommodate your new training data. So for this example, it has to overcome a loss of 6.22 to do this. Let's apply an optimizer over this loss to slowly reduce this loss so that we can see the model learn a brand new sequence. And here we have a training prompt that says who to subscribe to YouTube for machine learning, and the content is subscribe to, and the target response we want the model to learn is neural breakdown with AVB. Let's see if the model can do this. But before running this, let's see what the normal output of the network is without any fine tuning. The model outputs subscribe to the following YouTube channels for machine learning. So it's not saying my channel's name, but let's see if I can make it say the channel's name. First of all, we're gonna import the Adam W optimizer. The optimizer is a concept in PyTorch and in other deep learning frameworks like TensorFlow. The optimizer's role is to apply the gradient descent updates on the model parameters. Here, first I'm generating the input-output pair. Data input IDs, a sequence of integers, and data labels is again the sequence of integers, but the stuff that came from the prompt is turned to -100. So here we have the training loop right here. First we pass the data input IDs and we receive the output as the logits, and we have the output logits, and we call our loss function where we pass in the logits and the labels, and then we calculate the loss, and then we do loss.backward, optimizer.step, and optimizer.zeroGrad to train the neural network. And let's see if we run this, what happens. We are also printing out the losses here, and as you can see, the loss slowly goes down. It started at 1.17, now it's 0.001, but let's see if it actually learned it. To do this, let's just copy paste the this code again. We have already seen that this was subscribed to the following YouTube channel. Now let's do it after the training was done, and let's see if, oh well, now it says neural breakdown with AVB. Congratulations, you have now fine-tuned the LLM to say what you wanted to say. All you had to do is create this kind of structure, some prompts and the target response, and then with some tokenization and calculating the loss and all of that, you finally train the network to output neural breakdown with AVB. All that the model internally does is increase the probability of neural being the next predicted word after subscribe to and this entire prompt is inputted. But there's actually still a huge problem. You're basically fine-tuning all of the weights in the network, and what that means is that if you train on a new dataset that's much different than the original data that this model was trained on, it can lead to something called as catastrophic forgetting. The model might forget things that it had learned previously. Another problem is that because you're fine-tuning entire weights, which are probably 1 billion weights in the network, that will require a lot of resources. A lot of compute might go to train that, and also it might be costly to do it. A better approach to do this, however, is to use something called as a LORA adapter, which means low rank adaptation. Let's see what that means. Here's me from the past explaining how LORA works. Low rank adaptation, or LORA, offers an efficient alternative to complete fine-tuning. LORA freezes the original model's parameters and injects trainable low-rank matrices into each attention and feed-forward layer of the model. Suppose one of these attention matrices in the base model is a matrix of size 1024 by 1024, and we want to learn a new fine-tuned matrix from here. Instead of directly learning the new matrix, we are instead going to learn the residual matrix, which when added to the original base weights, return us the new fine-tuned weights. The big thing LORA does is, instead of learning the full 1024 by 1024 weight matrix, we instead will learn low-rank factorization of them. For example, if we do a rank 2 LORA, we are basically just training 4096 new weights to generate a matrix of million values. Given some input-output training data, we would want to use backpropagation to learn these matrices for all the attention and feed-forward layers. Now, if we have multiple different tasks to complete, we can train new LORA adapters for each task. The base model's weight was never really changed during LORA fine-tuning. We just added these adapter networks onto each of the attention and feed-forward layers, meaning that we can keep reusing the base model for all features and just attach these new feature adapters on top of the base model and make it specialize on these different tasks. And another amazing thing about LORA is that you can train multiple LORAs that all do different things. For example, here I can train a LORA adapter to predict the category of the paper, but I can train another LORA adapter that learns to predict, say, the number of citations that a paper might receive, or if or not that paper could qualify for a big conference or not. The base model still remains the same, so you can still use your LLM to do your other tasks as well, but when you need to do a specific task that is covered by a LORA adapter, you basically just plug it in and use the network with the LORA adapter. Programmatically, to do LORA, we have a library also by Huggingface called PEFT, which I think stands for Parameter Efficient Fine-Tuning. Basically, after loading your model and your tokenizer, you create this LORA config object, which tells you what the LORA should look like. For example, here we are doing causal LM, which is the task we're training on, and here importantly we say the target modules. We are basically saying the Q underscore proj and the V underscore proj of the model is what we are going to apply the LORA on. The Q proj and the V proj are the MLPs associated with the query projection and the value projection inside the attention layer. And then finally you call this get PEFT function where you pass in your base model, which you got here, and the LORA config, which you generated here, into the get PEFT model function, and that returns you a new model which just has 6 million trainable parameters compared to the 1 billion that the original model has. And you can change the value of R, which is the projection dimension, and that would reduce the trainable parameters even further and train an even smaller LORA adapter. And finally, if we rerun the experiment that we ran earlier with neural breakdown with AVB, let's see if the new model is able to also learn the same pattern. Another cool thing is that because you have a smaller number of parameters, you can kind of keep a high enough learning rate as well. Now 1e-3 is a bit much, but it will work for a small use case like this. And yeah, you see the loss go way down, and if you rerun the model with this, you see that indeed it predicts subscribe to neural breakdown with AVB. So with all that out of the way, let's begin to train. Let's see if our new model can overfit on a very handful of datasets. So I'm going to just train on 8 examples, and let's see if our model can overfit these 8 examples or not. Here you can see that before training, the accuracy on those 8 examples is just 0.375, which means 38% or 37.5% times it's actually accurate. So as you can see, the accuracy is going up as the model is training, which is all the validation I needed to go train a real model. So the accuracy went from being in the 30s all the way to 67% after I did the fine tuning on just 500 examples. So that's quite impressive, and I hope with more training data and longer training, it should be able to reach the 80%, 90% accuracy mark. So finally, before wrapping up, I also want to test this method on some existing archive papers. Let's go to archive and find a computer vision paper and find anyone. Let's say this fMRI analysis one. Let's go to this, and we'll copy the archive ID here. And I have a function that inputs the archive ID and internally calls the archive API to get the title and the summary of the paper. So if I just run Python inference.py, yeah, and it says the prediction is computer vision and pattern recognition. So here I am trying to see if changing the model ID to the original llama model before the fine tuning, if that also succeeds in classifying the paper correctly. Let's see what it predicts. So interestingly, that predicts it as machine learning, which kind of shows that the PEFT model that we trained does indeed is better at this job. Let's also try another archive paper from maybe NLP. Let's see, Math Coder 2. That sounds interesting. Okay, let's see that, and let's switch back to our PEFT model. Let's wait. Well, yes, it does predict natural language processing, which is right computational language, which is indeed the right key. So hopefully that sort of tells you something about fine-tuning. Again, this was a contrived example which I chose so that I'm able to show how fine-tuning works and all of the nuances that goes into fine-tuning. And obviously the specific example itself matters quite less because you can use this framework for any fine-tuning task. Well, that is it for this video. I hope you had fun. I hope you learned something new. I'll see you in the next one. Goodbye. Take care. You are magnificent. Bye.